Hello, welcome to today's class. Today's class again is on shared memory programming. This is the second class on this topic. In the last class, we talked about memory programming, and we saw how to create new processes in Unix, and we saw how to join processes, and then we saw how to allocate and free shared memory, and then we saw how to communicate using shared memory, and we wrote a program to add all the four numbers in an array using two processes. In today's class, we will see how to coordinate access to shared locations, and we'll talk about mutual exclusion and locks. So I would like to start with a program. So in this program, we allocate shared memory, and the shared memory is pointed by I. So I is a pointer to the shared memory, and we create 9 new processes, so that in total we will have 10 processes. So we have a shared memory that is pointed by I, and we also have another variable j, which is not a shared variable, and each of the 10 process will have a copy of j. And now after we create the 10 process, each of the 10 process will be executing this code. Actually, all the 10 process will also execute join process. So this code will be executed by each of the 10 process. And in this code, we are first storing the ID of the process in the shared variable, and we also store the same ID of the process in the variable j. So the first value ID will get stored on a shared variable, and we know that there is only one shared variable that will be shared by all the 10 process, whereas the second value in the second statement, the value ID will be stored on the private copy of j. Each process will have its own version of j, and then we check whether I is equal to j or not. Not I, whether we will check whether the memory location pointed by I, that means we check whether the shared variable is equal to j or not. Now in normal sequential code, it will never be the case that star of I is not equal to j, because we are assigning the same value ID to star of I and also to j. So in sequential code, star of I will always be equal to j, and hence we will never print this error statement. However, now when we have multiple process, it may happen that star of I is not equal to j, and hence the error message may get printed. But how can that happen? How can it happen that star of I is not equal to j? To explain that, let us assume that process 2 executes this statement. For process 2, its ID will be equal to 2. So when this statement is executed, 2 will be stored on the shared variable, and then process 2 continues and execute the next statement, and when the next statement is executed, the value 2 will be stored on the private copy j of j in process 2. Now let us assume that before process 2 is able to execute this if statement, process 5 gets scheduled to execute. So before process 2 can execute this if statement, process 5 executes this statement, and when process 5 executes this statement, the ID of process 5 is 5. So 5 will be stored in the shared variable, whereas the private variable j of process 2 remains as 2 only. So later on, when process 2 comes back and try to execute the if statement, we have a situation where the shared variable have the value 5, whereas the private variable j of process 2 is equal to 2, and hence star of I will not be equal to j, and the error message will be printed. To explain it little more, I'm showing the shared variable here. I points to the shared variable, so star of I is the shared variable, and after process 2 executes these two statement, the shared variable will be equal to 2, and the private variable j of process 2 will also be 2. There's a small typo, this should be process 5. So this is j in process 2 and this is j in process 5. Every process will have its own copy of j. So after process 2 executes, this is the scenario, and now before process 2 executes the if statement, we said that process 5 gets scheduled and process 5 executes these two statements, and when process 5 executes these two statements, your shared variable will become equal to 5, because for process 5 the ID is equal to 5, and the private copy of j in process 5 will be equal to 5. And now later on, when process 2 comes and tries to execute the if statement, we have a situation where the shared variable have the value 5, whereas j in process 2 have the value 2, and they are not equal, and hence the error message will be printed. Now if we look at this program, there is only one statement where j is assigned the value, in this case id into 2. So there is only one statement between the two statements where a value is assigned to the shared variable, and the value from the shared variable is used in the if statement. And to execute this single high level language instruction, it would take less than 1 microsecond. So only if process 5 gets scheduled within this 1 microsecond, then only we will be able to see the problem. So so it may be very unlikely that we will actually see the error when we run the program. So maybe if we run the program many number of times, after many execution, we may once see the error, because the process 5 should get scheduled between these two statements. So between process 2 executing this statement and process 2 executing this two statement, between that time the another process should get scheduled, and then only we will see the problem. So it may be difficult to reproduce this error if we have only one statement like this. So for us to be able to reproduce the error, what we will do is, instead of this single statement, we will replace this single statement with a for loop, and in this we will loop 20,000 number of times, and each time in the loop we are doing the same computation. So we put this loop only to increase the amount of time between these two statements, so that when we have uh, more time between the two execution, there is more probability of a process getting scheduled, and there will be higher probability of the error occurring. So this is just to reproduce the error that we are using a for loop. And hence now this is the program that we have, and if we now try to run this program to see if we can reproduce the error, so here we have the programs, and let's look at program number 4. And this is the program where we are assigning a value to the shared variable, and we have a if statement where we check the value of the shared variable, and in between we have some amount of delay. And now if we try to execute this program, first let me compile it, and let me compile. So it's compiled, and now let me run the program. And when we run the program, we see that an error has occurred. So out of the 10 process, the error was seen for 3 process number 0, process number 5, and process number 9. So what happened is process 0 stored its ID to the shared variable and also to its private copy of J, but before it can execute the if statement, the value in the shared variable got changed to 2, and hence it printed the error. And similarly, error occurred for process number 5 and process number 9. If we rerun the program, this time it happened for process number 6 and process number 5. I run the program again, and this time it happened for 1 entry. So the error happens only if between those two statements the process gets swapped. So only then we will see the error. So different runs we may see the error for different process. Now going back to the slides. Now I have another program, and in this program we initialize the shared variable through the pointer variable I. We initialize the shared variable, actually this should be star of I. We initialize star of I to 0, and then we create 2 processes, and each of the process will try to increment the value of the shared variable by 1. So we create 2 processes. Both the process will execute this statement. So process 0 will execute the statement which will increment the shared variable by 1, and then process 1 will execute this statement, and again the shared variable will be incremented by 1. And since we started with the initial value of 0, if the shared variable is incremented 2 times, at the end we should see 2 being printed here. However, we may not always see 2 being printed. And why would that happen? Because we have only one statement. We have only one high level language statement. So how can it happen that the process gets swapped during the execution of this statement? What actually happens is when we compile this high level language program, this single high level language statement may be converted into 3 machine language instructions, I am showing the corresponding assembly language instruction here. So this high level instruction is incrementing the value of the shared variable pointed by I. So to do this increment, first we have to load the value of the shared variable to a register, then increment the value of the register, and then store the value from the register into the shared variable. So this single high level language instruction will be converted to 3 or more machine language instructions. And now when we have multiple number of instructions, the process may get swapped at any of these instructions, and we have a scenario similar to what we discussed just now. To explain it further, let's say we have these two processes, and process 0 runs in core 0 and process 1 runs in core 1. Now each of the two cores will have its own register R0. So core 0 will have a register R0 and core 1 will also have its own copy of register R0. Initially we don't know what the value of these two registers are, and here I am also showing the value of the shared variables. This should be star of I. So the value of the shared variable is initialized to 0, so it's 0. And now since these instructions will be executed by process 0 in core 0, and the same instructions will be executed by process 1 in core 1, and since we have two different cores, the execution will happen independently. So it may happen that process 0 starts executing first, and at that time process 1 has not yet executed, and when process 0 executes the first instruction, it will load the value of the shared variable to R0, and process 0 belongs in core 0, so R0 of core 0 will be modified. What will be the new value of it? Whatever is there in the shared variable, that will be loaded to R0, so R0 will become equal to 0. And now process 0 will proceed to execute the next add instruction, and now let us assume that at this point process 1 also starts executing the first instruction, which is the load instruction. So now process 0 will execute the add instruction, whereas process 1 will execute the load instruction. When process 0 executes the add instruction, the R0 will be incremented by 1. So R0 of R0 of core 0 will be incremented by 1, so this register will become equal to 1. And when process 1 executes the load instruction, the value from the shared variable will be loaded into register R0, and since process 1 belongs to core 1, the value from the shared variable will be loaded into R0 of core 1. And these are the changes we see. R0 in core 0 changed to 1 because of the add instruction, and R0 in core 1 changed to 0 because of the load instruction. Now process 0 and process 1 will proceed. Process 0 will now execute the store instruction, whereas process 1 will execute the add instruction. Because of the store instruction, the value from R0 will be loaded into the shared variable, and since this instruction is being executed by process 0, the register R0 of core 0 will be stored into the shared variable. So the shared variable will become equal to 1, and at the same time process 1 is executing the add instruction, and hence R0 will be incremented by 1, and this R0 is the R0 of core 1. So R0 of core 1 will be incremented to 1 because of the add instruction, and that's what we see happening. The value from R0 of core 0 is stored into the shared variable I, and at the same time R0 of core 1 is incremented to 1. Now process 1 proceeds to execute the store instruction, and when the store instruction is executed by process 1, the value from R0 will be stored into the shared variable, and since process 1 is in core 1, the value from R0 in core 1 will be stored into the shared variable, and since this is 1, the shared variable will continue to be 1 only. So by this time both the process have executed this increment instruction, both the process have completed execution, and now if we look at the value of the shared variable, it's only 1, whereas it should have been 2, but it is only 1, and that happened, the problem happened because whereas process 0 was, before process 0 could complete incrementing the value of the shared variable, process 1 also entered into this code, so it did not get the updated value of process 0, but it used the old value of the shared variable, and this was creating the problem. So this kind of problem can happen in shared memory programming. If we don't coordinate the access to the shared variable, we can have problem like this. So we need a mechanism to coordinate the access to the shared variable. Access to the shared location must be properly coordinated, and what we mean by that is that if one process read a location with the intention of updating it, the process must ensure that no other process reads that location till that process finishes the update. And how can we achieve this coordination is through locks. So locks are primitives that ensure that certain blocks of statement are executed by only one process at a time. If a process is within such a block, no other process should be allowed to enter the block. So locks enable us to implement mutual exclusion. Here we have a code that use locks to solve the problem that we saw earlier in our discussion. So here we allocate a shared memory for the lock. The lock itself has to be in the shared memory because multiple processes will share it. So the lock has to be in the shared memory, and so first we need to allocate the shared memory for the lock. Next we need to initialize the lock using the lock init call, and after initializing the lock, the processes should acquire a it should acquire the lock using the lock function, and after acquiring the lock it will execute the critical section, and after finishing the critical section the lock will be released. So we acquire the lock using the lock call, and we release the lock using the unlock call. And before entering the critical section, the process should acquire the lock, and after completing the critical section, the process should release the lock. So the first process that is able to acquire the lock will enter the critical section and execute the critical section. And while the lock is owned by that process, any other process that tries to acquire the lock will be blocked. They will not be able to enter the critical section. And all these processes will be blocked in this call, and only when the process that is within the critical section release the lock, only at that time one of the process from this list of process that are waiting on the lock will be selected, and that particular process will be able to enter the critical section. So in this way we can coordinate the access to the shared location, and at the end of the program we need to free the shared memory like we did before, and in case of the lock we also need to free the semaphore. So this program shows how to use locks. Again, let us run this program. So we have program number 5, which use locks to coordinate access to the shared variable, and here we allocate the lock and initialize the lock. Here we acquire the lock, and here we release the lock. So now, since only one process will be able to execute the critical section, the error should not happen anymore. The value of the shared variable will not change, because there is only one process that is executing the critical section. Between the time that the shared variable is updated and when it is checked in the if statement, there is only one process, and hence its value will not change, and hence the error will not happen. So let us try to execute this program. Let me first compile it, and then when I run, this time the error do not happen. I am executing it multiple times and the error does not happen. So in this way we can coordinate the access to the shared memory using locks. If we don't coordinate the access to the shared location, we may encounter errors like we have seen in 2 of the examples. So with that, I'd like to end today's class. If you have any questions, you can please post it through Piazza. Okay, thank you. Bye.